Welcome, dynamics students. This is our final mini lecture on moment impulse for particles, and we're going to be really leveraging our treatment of the linear and angular momentum of a system being the sum, basically, of its composite parts of the linear or angular momentum of one part plus that of the other, and the fact that unless acted upon by a force, in the case of linear momentum, or a moment, in the case of angular momentum, the system momentum, whether it's one big part or composite parts, isn't going to change with time. And if it does change with time, it is according to the impulse imparted by the force of the moment. We're going to really leverage this idea of composite parts up and apply the concept of impulse momentum to a moving fluid, which can be thought of as like a little bit of fluid that could be represented by, totally accurately, if it was small enough, by a particle at its center of mass and adding up over an entire range of fluids, which might just happen to have a velocity in a given direction, maybe being conveyed through a pipe or any other kind of container or channel. So again, this is a little bit of an extrapolation of what we've already done in terms of systems of particles, groups of particles, and the method of composite parts relating a body in its entirety to momentum or position mass of any one part of it. Okay, so we're going to do a real quick recap of Euler's law. So we know that the force resultant on a body is the time rate of change of linear momentum of the body, capital L, and the resultant moment about a reference point O applied to that body is going to be the time rate of change of angular momentum, big H, capital H, vector quantity about point O with respect to time. This applies, remember, our first derivations of using Euler's first law. It was very important that this didn't require that a body be rigid, only that it be a body with a constant mass. So we're going to really leverage this and apply it to a fluid. So we're going to use two big concepts in this lecture. We're going to use our standard impulse momentum, which says our linear or angular momentum of a system at a given time is going to be the same as the linear or angular momentum of that system at another time, unless it's acted upon by a force or moment, in which case the difference is simply going to be the impulse of that force or moment. So we're going to use that concept plus a new concept, which is called a fluid reference volume. So we're going to look at the idea of the amount of fluid, the body of fluid, even if it's moving, the volume of fluid that would at any instant be occupying the inside of a portion of a pipe or an elbow or a T or any other kind of container or a channel. So this is a common tool in fluid dynamics called a reference volume, and it's a way of applying dynamics of bodies to something that's moving all the time. We take a snapshot in time and say, in that instant, it's got this volume. It's got a certain density, therefore it's got this mass. And I can treat it like a body from the viewpoint of applying our Euler's law relationships, which then allows us to write all kinds of expressions of impulse momentum, just like we would for particles colliding. And in fact, you'll see something that looks very similar to the idea of impact, where we have an intermediate state. Okay, so let's make some pictures of this fluid reference volume. So say we have a pipe, and we got water flowing through the pipe, and so we'll define something that's used in fluids a lot. It's called a flow rate, and this is a volumetric flow rate. So it's volume per unit time, gallons per second, or acre feet per day, or whatever your units of choice. So the pipe has an inner radius of r, and if we look at, say, a point of interest along the pipe here that we care about for some reason, it's between x1 and x2 along the length of the pipe. We could imagine the pipe is gone and there's nothing but a cylinder of water. Now, because the water is moving all the time, the water molecule that might be present in that cylinder is always changing. It's another piece of water. It's another molecule. It's another little mass unit. But at any given instant, if you were to carve out this reference volume, it would literally be a cylinder of water that looks like it was like cast from a mold of the pipe itself. And we can call that a control volume. And it's got a shape, it's got a mass, it can be acted on by a force, it can be accelerated, momentum impulse applies to it, all kinds of cool stuff we've already learned. And we will only have to deal with the fact that it is actually a snapshot of a moving fluid as we step through application of our impulse and momentum. But at this point, we just think about it as it's just a body. It's a ball of water with a certain shape and mass. And we can remember that the mass of this control volume is related to its density times its volume, because the volume is taken from the container that formed it. Okay, so what kind of things would apply forces to a control volume of fluid? The container, literally, is the only thing that touches it. Gravity, yes, but for the most part, we're going to be looking at, we will sometimes apply gravitational force to it, of course, but a lot of times we'll be looking only at forces that are imparted by the container on that at a time. And in fact, usually we will have equal normal forces coming from the container that counteract gravitational forces. But basically will be, for the point of view of this particular discussion, the forces we'll be interested in with the moving fluid are those that are applied by the pipes, connectors, fittings, especially something that's trying to make that flowing water change direction. This is a particularly useful application of impulse momentum. So we're going to start with a 1D example. Many of you might know that moving fluids moving through pipes and other containers are subject to frictional forces like anything else that moves, and that's a big deal when you're designing water systems. And in fact, you need to over-pressurize in some cases parts of it near a reservoir or a well pump station to ensure that something at a far branch that's been subject to a lot of frictional losses will have enough pressure that it can meet fire requirements, etc. Even though the whole system is closed and not leaking, the velocity of that water coming out the end is not going to be coming maybe the same given the same pipe area, but we won't have the same pressure that we might need to supply a fire truck. So frictional forces are going to act and reduce the acceleration of the fluid going through the pipe. So we can apply Newton's second law by doing an FBD of this reference volume. So here's the reference volume of fluid's flowing through, and in any snapshot we got something going through. It's got a velocity. Frictional forces are acting backwards to the flow rate. So we can say that the mass of the fluid times the acceleration in the x direction along the pipe is equal to the sum of the forces, the friction applied by the pipe. So okay, we can substitute in what we know about our reference volume mass. It's the density of the fluid times that reference volume. And now we have a Newton's second law expression for acceleration, which is the time derivative of linear velocity. And now we're looking like we can set up for an impulse momentum. We have the bare bones of an impulse momentum expression, because A is dV x dt of that fluid. We could integrate with respect to time and get maybe a velocity change. So let's look at this for water flowing into and out of a very frictiony pipe system. So I'm going to zoom in on this section to just show the diagram a little, this little hand sketch. So let's assume that we've got a pipe and water's flowing through the pipe. So here's our pipe. And it's going, in the x direction. So out here, there's very little friction. We're just not gonna worry about it, but maybe we've got some kind of coupler here, and it's got a lot of friction. So we want to understand what has happened to this fluid between the packet of fluid that's going to enter this frictiony pipe and the packet that's going to exit it. So because we know that there's going to be a substantial amount of force exerted on the water that's in the pipe, and we want to use our momentum impulse relationships to see if we can't calculate that based on something that we could measure. And we're not losing any water, so our flow rate is the same. This is called otherwise known as steady flow. So the volume of water per unit time entering the frictiony pipe is equal to the volume of water exiting. So if we want to look at a little differential length of water in the pipe, a little slice of water in the pipe, the inner diameter of the pipe is A1. Out here it's A2. These could be the same, they could be different. If we imagine a little differential length of water along the pipe, S being length along the pipe, we have a DS1 and an A1, which if we multiply together gives us a differential volume of water entering the frictiony pipe, and then the same with DS2, A2 exiting the pipe. If the A's weren't the same, the S's wouldn't be the same. We got to have the same volume coming in and leaving in an instant of time. So we've defined, because we've got a constant density, we've defined a mass going in and a mass going out, and then we've got this reference volume of water that's always existing within the pipe, and any volume of water in that pipe can be subject to the frictional forces pushing backwards in the pipe. So let's look at that as a body, okay? Just a bunch of bodies. So we got an entering body, our with some velocity. So we have our dm1, which is our ds1a1 coming into the pipe, and it's little. It's a differential little body because dm, it's got a differential thickness along the pipe length. And then we have a dm2 exiting at v2, and then between those we have this reference volume of fluid that can be acted on by the forces on the pipe. It's got some mass, we'll call it mass of the reference volume, and it's got some velocity. We don't know what it is, we'll just call it V reference. But it's only this reference volume that is subject to the forces, so impulse can be applied to the reference volume, nothing else. Okay? So we're kind of set up to think in terms of impulse momentum. We could say maybe the momentum, of this body, and relate it to the momentum of this body. There's been a change. They're the same volume. They're going to have different velocities, and something in here is happening to the reference volume with a force impulse that is somehow going to change V1 relative to V2 if it's non-zero. And we're saying it's frictiony, so there's a high coefficient of friction in this pipe, so there's definitely a force impulse. This should be sounding a bit like that maximum deformation state in an impact, where you have impulses being imparted, one particle on another during an impact, and they're together, and then they come out at a different velocity having been acted on in that intermediate state. The reference volume is a bit like the intermediate state of max deformation in an impact of two particles. So not quite the same, but kind of along those same lines as having that in-between state where you can have forces acting. Okay, so let's go back to thinking of the fluids as moving with time. So we're going to take time t, initial time. We've got the pipe filled with fluid, it's moving, so we've established a reference volume with a mass m reference. And it can be acted on by a frictional force, but it hasn't yet. We've got an entering packet of water, and it's got a mass of dm1. It's got a volume of A1 times ds1, and it's got a density, so that gives us a dm1. And it's got a velocity 1. So our total momentum at time t is the momentum of the entering packet times the momentum of the reference volume. So, plus the momentum of the reference volume. Plus. So, system momentum time 1. So then the fluid moves through the reference volume, and you can think about it as that entering packet of fluid gets spat out the other end. The reference volume's still full of fluid. We haven't emptied it anywhere, so we've just kind of, it kind of like a ball moving through a tube. If you push one end on the inside, if the tube's full of balls, one comes on the outside. And that's how electrical current is sometimes described, as the movement of electrons through a solid. So we've had the movement of water. But in moving that water, we've allowed that frictional force to operate on the reference volume. So as that packet of water moved through the tube, an impulse was delivered by the tube walls to the reference volume only. So we can look at this as an after state at t plus dt. We don't have that forward packet. It's moved on through and is now kind of resulted in the emergence of a packet at the back end, which has the same volume because we have Q1 equals Q2, we have steady flow. So whatever the area 2 is, we have to adjust our DS2 such that we keep constant volume. Density hasn't changed. We're not allowing for any phase changes, or nothing got heated up or anything. And the momentum of our reference volume is just going to be m reference times v reference minus the impulse that was delivered by the force. And because we're only operating in dt, we're not going to represent this as an integral. It's just the force times whatever time we had, and that time was dt. So it's not integral of f dt, it's just f dt. And that's important because we're looking at a snapshot in time of the flowing fluid. So that's a little bit different than maybe a time of a collision that actually is a finite amount of time. This is an instantaneous snapshot, similar to maybe a differential length unit along a beam changing, or differential time unit. But anyway, this adds up to this whole expression is our momentum at effectively time 2 t plus dt. Now we know that given the fact that we have accounted for the action of the force resultant, this momentum should equal the initial momentum because we've already accounted for the impulse. So conservation of momentum works in this case. So we can say momentum at time t equals momentum at times t plus dt. Tally it all up, and we find that our reference volume momentum, which we have no idea what it is, cancels out, which is really good. And so we have an expression for the mass of the entering packet of water times its velocity equals the mass of the exiting packet of water times its velocity minus the impulse delivered in that time instant by the force exerted by the pipe on the reference volume. Okay, we can simplify and we can just call these terms dm because they're the same by steady flow, and then we can divide the entire expression by our time packet or our time snapshot dt, and we end up with dm dt times v2 minus dm dt times v1 equals the force resultant. And dm dt again is going to be, it's called a mass flow rate, and if we remember, mass is equal to a volume per unit, volume times density. Volume per unit time is flow, big Q. So dm dt equals the density of the fluid times the flow rate. So we have that. So we basically have the density times the flow rate times the difference in the entering and exiting velocities is equal to the force exerted by the pipe. Now, if we want to look at that from okay, why do I care? Yeah, we've got a velocity reduction. Maybe that's a problem if we have to convey the water somewhere. Something that's important for us is this pipe section. Action, reaction, Newton's third law says, okay, if this pipe is exerting a force in this direction, frictional force on the water is exerting a force on the pipe this way. So if this pipe's just laying on the ground, say, and the ground can't exert enough friction on it, the pipe's going to start to move. And if we're relying on it, saying, being attached to a building or some fixture, it's going to be yanking away. So we need to secure that down to make sure that the impulse that it delivers can be reacted against by some kind of fixture or structure. And that gets even more important when we're redirecting flow in multiple directions. So that's the next example we'll use. So once again, important thing, once we've got a force being exerted by that reference volume due to momentum change and impulse, then we've effectively got a force being applied to our pipe, our elbow, our container, whatever, and we need another force being exerted by something else to keep it from accelerating. We don't like our piping system to start accelerating. That can cause all kinds of problems. Worse when it's filled with flammables. Okay, so let's look at a couple of different directions, and let's look at the effect of moment. So let's look at a fluid this time that's being diverted. We're going to change not just its speed, but we're going to change its direction. So we're going to look at a 2D problem. So we've got an elbow, and the elbow has got some kind of center of mass that we can define. We can look at the fluid-filled elbow. If we can take the like the brass fitting or steel fitting away and just look at the water that filled it up, that's going to be our reference volume. So you're going to have water entering the elbow here, where we show the Q1. There's going to be a plane, in this case circular plane, that is the entry point of the elbow and one for the outlet. Likewise, and we can look at, again, a differential volume of water that's entering here by basically doing like a little packet. I'm trying to draw a little disc of water entering. We have a DS1 here coming into the pipe. So we can again define a differential mass unit of water ready to enter the reference volume area, and then because we have Q1 and Q2 equaling one another in steady flow, that same volume or mass, constant density, an instant in time later will exit the elbow. And what comes in goes out the other end. The reference volume remains filled with the same amount of water all the time. So let's just apply system momentum to this curvy reference volume. We've got a few more considerations, and we're going to look at point O down here in space, and we're going to consider the radius from point O, and we're going to look at the impact of moment or torque on the reference volume and the entering and exiting packets and subsequently on the fixtures. So we'll have two considerations: conservation of linear momentum and conservation of angular momentum. And we're going to find that this reference volume is acted on by both forces and torques. And of course, then they're going to have a reaction. So let's step back and just take our entering snapshot. We've got a packet of water ready to enter the elbow. We have the elbow filled with water, which defines our reference volume of water that's shaped just like the elbow. So let's write an expression for its linear momentum. So we have our entering mass, A1 ds, times the density of the water, times the volume up here at 1, plus the momentum of the reference volume. And this is going to be, we're looking at 2D, so this V ref and this V1, they'll both have components in the I hat and the J hat direction, no problem. Probably we know what those are because of the shape of the system. We're assuming laminar flow, so we're assuming the velocity is kind of in the direction or substantially in the direction of the container shape. So tangent to the container. And that's it. This is our entire linear momentum expression at initial time. So there we go. We're outlining that. Okay. So let's define an angular momentum. So how do we do that? Remember the relationship between angular and linear momentum is just we identify a point remote to the body. In this case, it's going to be the entering blob of water and the reference volume of water. And then draw radius vectors, cross R from the reference point to the point of interest. And in this case, it's the center of mass. because we're looking at momentum, we don't want just any point. We want the particle that represents the whole body. In this case, we got a body that's a blob of water entering the pipe, and we got a reference volume, which is a very particularly shaped blob of water. If we want to apply impulse momentum to these, we're going to have to approximate them as, represent them as particles, which means those particles are going to have to be at the center of mass. No problem. We got a circular little disk out here of differential thickness. So the center of mass of our entering blob of water is at C1 here, which is the center of that opening of the elbow, kind of right in the middle of where we're going to enter the reference volume. And we'll have to define the center of mass of the reference volume by the shape of the spigot. Or spigot by the elbow. So we'll have to know that via the elbow. That would be information we were given or that was pre-calculated. Okay. So we can define some point in space that we know where that is relative to C reference and C1 and just define a cross product. So defining the angular momentum as R cross L. So we have the linear momentum of our entering packet, and then we have the linear momentum of our reference volume. We're going to cross those radius vectors in. So here's our H0 time 1, big H, angular momentum. Okay. So at time t plus dt, over our instantaneous snapshot of dt, the container that's defining that reference volume is going to exert a moment and a force on the reference volume, and in that same dt we will have moved a volume of water equal to this A1 ds out the other end. Depending on the relative sizes of A1 and A2, the ds will either be greater or lesser or the same. So we can do an after a t plus dt linear momentum. Again, we got our reference volume momentum. We've subtracted the impulse of the container, which again, this will have probably components in the I hat and j hat directions just because of the shape. And now we've got a blob of water coming out the other end, so we've got its linear momentum v2 dm2. And our angular, all we have to do is take cross products from our reference point. So we're going to do R from our 0 absolute inertial reference frame point outside of the elbow somewhere to C reference, cross that with our linear momentum of our reference volume of water. And we're going to subtract the same. We're going to cross everything up here with R. So we're going to look at the impulse moment that elbow exerts. So it's the same as the force impulse, but with R from our reference 0 point to the center of mass. So it's R 0 to center of mass cross F, otherwise known as the resultant moment with respect to 0. So it's mr sub 0 to the reference point in the reference volume, the thing that looks like the elbow, dt. So it has dt in which to operate. And then we're going to add our angular momentum of the exiting packet of water. So it's linear, crossed with the radius vector from our origin point to the center of mass of the exiting packet, which is right in the middle of the plane of exit of the reference volume there. So our from point 0 here to point C2 crossed into our linear momentum of our exiting packet. Okay, so not surprisingly, if we tally these up, our reference volume angular momentum expressions end up canceling out. So we end up with and if we use our relationship that our mass flow rate dm dt is just equal to density times the volumetric flow rate, we can write a simplified, I've skipped a couple of steps just doing the simplification, but we can write a linear momentum expression for the entering and exiting water. as our mass flow rate times the entering velocity. And again, this will probably have an I hat and a J hat component, plus the force that's being applied to the reference volume, and it'll have probably an I hat and a J hat, and then the mass flow times the exiting velocity. So if we measured, we don't have to get some crazy force strain gauge out there. If we have some kind of flow rate, we know the area, we can easily measure these two velocities. We can measure it through flow or other types of methods. So upstream, downstream velocities, we know what the mass flow rate is, we know what Q is in the density. We can calculate what force we are going to have on that elbow and in what vector direction. We're going to take the vector direction by an assumption of the velocities based on the shape of the system, or V1 and V2. So, this elbow is going to want to go flying off somewhere in this direction very likely. And so we'll have to restrain it to keep it from doing that. But that's not all. It's going to want to twist somehow and probably try to pry itself up at this corner, possibly causing a bad leak. So we might need to know what the resultant moment that the elbow has to exert on the reference volume in order to effect the change in direction and reinforce that attachment point, in response so we don't get a leak. So we just do the same thing with angular momentum. We tally up the after angular momentum versus the initial angular momentum. Our R0 to C center of mass of the reference volume crossed into our linear momentum for the reference volume. Those cancel out, and we're just left with an expression for the sum of the moments applied to the reference volume based on moment around point O is the mass flow rate times the radius vector from our reference point O up to the center of mass of the entering packet of water, crossed into its velocity, plus mass flow rate times the radius from our same origin point in our inertial reference frame outside of the elbow up to the center of mass of the exiting packet crossed into its exiting velocity. Again, this can be measured based on geometry. This can be measured with a mass flow rate and a knowledge of the exiting area and a knowledge that we have steady flow. Same with these two. We can measure mass flow rate with an understanding of our volumetric flow rate and the density, and we now know the moment being applied to the reference volume by the container, which is again being acted on in the equal magnitude and opposite direction on the container. In this case, it's the elbow by the reference volume of fluid. So basically, we are having eventually to apply forces and moments to the container holding the reference volume in order to achieve the change in linear and angular momentum of the entering versus exiting packets of water with every dt. It's continuous. So those forces and moments need to be applied to that fitting, or the fitting is going to go accelerate or even accelerate just a little bit and gap, and then we have a leak. So that Newton's third law is kind of the cinch point that we may redirect the fluid, no problem, but that reference volume of fluid through which forces and moment impulses are being applied to redirect the flow or slow it down. It's not going to speed it up. It might slow it down. Friction is usually the only thing that applies. That's being applied by a fitting, by something solid, which is upon which the reference volume of fluid is going to push back. And most of the time in our design, we need to be really concerned with the push back and make sure that the fitting is adequately supported. So if you've got a big pipeline with a high Q, some dense fluid moving at high speed, high flow rate, and you need it to make a bend, you definitely are going to want to pile up some supports pushing back against that bend, or that bend could end up breaking off and starting to accelerate as the moment or force impulse from the fluid redirecting that flow isn't being counteracted, and so your elbow fitting is going to accelerate, which you don't want. So that's a practical application that is sometimes forgotten in, especially in water distribution systems. Water's got a pretty high mass. Notice this mass flow rate is a multiplier by these angular momentum changes. So the higher the mass flow rate, the higher the moment or the higher the force necessary to achieve any change in momentum or any change in velocity. So dense fluids are definitely going to be more of a challenge for the fittings containing them and redirecting them. So that is an example of impulse momentum basics, being able to take any kind of body. Boy, we've diverted completely from rigid bodies. We used a fluid. So this was the ultimate application of Euler's first law to represent any kind of body as a particle at its center of mass if it's translating. And so even though we invoked angular momentum, each of those packets of fluid was translating and moving. And we could just look at it as in terms of its center of mass. And in the case of the reference fluid, it was just standing still effectively from the standpoint of our solution. So that is the concluding concept in particle impulse momentum. And after this, this dynamics course is going to dive into rigid bodies. And we won't be using deformable bodies. We'll be using a very restricted subset of non-particles. So we'll be looking at rigid bodies in planar motion. And so we'll go back and reapply kinematics, kinetics, work energy to something that is now rigid, 2D, and can rotate. So we'll be picking up a lot of new concepts with that. So stay tuned.